Okay, hello everybody. Hopefully you can hear me. So today we're doing a webinar about, oops, we have some questions already. Okay, good. All right, good. Okay, so today we're doing a webinar on the multiprocessing support within Python. All right, and just to let you know, this entire webinar will be recorded, and it will be put on our website at develop.com/webcasts, plural, and you can find lots and lots of different webcasts that we've done over the years on all kinds of topics. And you'll get an email in roughly 2 days that will have a link to this video. All right. So anyway, this is me. It's a terrible picture, by the way. I don't know what kind of face I'm making. So my name is Pinku Surana, and I'm an instructor at Developmentor. And I teach C# classes, Python, MongoDB, architecture, and a few other things. All right, so let's get started. And if you have any questions, go ahead and pop them into your GoToWebinar interface. It has a section called Questions, and whenever I notice the little flag, I'll go over there and answer your questions. Okay, so the the problem with Python is that it is it's an interpreter. At least the C version of Python, it's an interpreter, and it was designed like 25 years ago. And when they designed it, they had written it to be a single-threaded application. And the way the interpreter works is that there are a bunch of global variables or global values, and in order to make sure that that everything works okay, they take what's called a global lock. So they call it the global interpreter lock, the GIL. And if you do a search for Python GIL, you will see zillions of blog posts and articles and so on complaining about the GIL. Okay, but essentially it's like a mutex, but it's just one big mutex that locks everybody out. So that only a single thread can run at a time. The end result then is that when you run a Python program, it will only use one core on your machine. So even if you buy some high-end, super amazing Xeon chip, which has 16 cores and then hyperthreading, so 32 virtual cores, Python will only use one of those virtual cores. Okay, and the other 31 go wasted. Now there are some small exceptions here. As you can see, that there are some C extensions that can release the lock, the global lock, while they're doing some big operation. Okay, and so NumPy is a pretty good example, but there are quite a few sort of number crunching C extensions where they can do things on a different thread while your main Python thread is running. Now, there is a threading library for Python, but unfortunately this doesn't actually use any threads. Instead, it's called cooperative concurrency, and in what they're doing is they're using a single operating system level thread, but they're trying to interleave the execution of different Python fake threads. So if you have 3 Python fake threads, thread 1, 2, and 3, then what they'll do is they'll take the real operating system thread and they'll say, okay, run a little bit of fake thread 1, and then switch to fake thread 2 and run a little bit, and then switch to fake thread 3 and run a little bit. Okay, but still everything is running on a single native thread. All right. So just to show you the performance here, I wrote a little program which computes pi by using what's called the Monte Carlo method. And essentially it's going to run this loop, let's see, 1, 2, 3, 5, 6, 10 million times. And it's going to produce random, coordinates. And then it looks at the ratio of coordinates that landed inside the circle versus coordinates that landed outside the circle. And by doing that enough times, you can get a good approximation of pi. Okay? So let me run this, but let me also show you my activity monitor. So I've limited it to Python processes. So right now I don't have any Python processes running. So I'm going to run Python 3 with my sequential version of Pi. Here we go. And you can see that it has, it says 92% of CPU, but really it's only using one CPU. The way the Mac reports the time is its percentage of a single CPU. Okay? And I wanted to time it, so let me just time it here. And also you can look at down here the system and user time. The user time does not go up to 100%. It's only at 50% because one core is being pegged with GoToMeeting, and then the other core is being used by this Python program. And the time that it took to compute pi, you see I get 3.14, 248, and the error is not bad, right? And the time that it took is 5 seconds, okay? So this is a sequential version of computing pi. And, just to show you, by the way, I thought this was mildly interesting. There's another Python runtime called PyPy. And because this is a compute-intensive operation, PyPy is actually, the regular Python is just an interpreter, but PyPy is actually a JIT compiler, the way that Java and .NET work. So we can take a look at that time. And you can see that it computed pi in that's the real time, but the user time is 0.54, so half a second, compared to the user time up here of 5 seconds. So about 10 times faster. Okay. Let's see. So we have a question, isn't PyPy for 32-bit only? I'm actually not sure. I'm not sure about that. All right. Okay, so let's get back. So we can see then that, hopefully you can see that Python only takes up, can only use one processor. Okay? So they have a library called Multiprocessing, and we can just go to the web page. Where is it? Here it is, Multiprocessing. So in this, on this page, they explain, how to use all the different pieces. So this is what I'll be going through in the next hour. All right? But all the documentation is here for you to look up later on. Now, so what they're going to do is, in order to get around the global lock, what they're going to do is spawn off or fork independent Python processes. So there are no threads being created here. Instead, it's literally creating more instances of Python. Just as if you had typed into the command line, if you had run Python like 5 times at the command line, that's what they're doing, is that they're going to run different Python programs, right, completely independent. There's no shared memory because the operating system doesn't allow, different processes they're all protected. And within each of those processes, there's only going to be one thread, all right? Let's see. Okay. Now, in order to pass data between these processes, it uses the default pickle serialization within Python. And this is handy because the pickle serialization can handle almost everything. However, from what I've been reading, there are a few problems in trying to pickle certain data types between Unix and Windows. All right, but typically it's going to work just fine. Okay. The multiprocessing library also has a support for managed shared data structures, which we'll see towards the end of this talk. Okay. All right. So the easiest way to get started with multiprocessing is with a class called pool. All right. And this is a high-level library which is going to automatically, not quite magically, but almost, it'll automatically create any number of processes that you want. And then you say, okay, I've got all this data I need to work on. So it will farm out the data to all the different processes so that they get, all the work done. And then it will collect up all the results. From a user's point of view, using the API, it's really, really trivial. There are actually two main ways of using it. The primary way is with a map function, and I'll show you how that works. They also have an async I think it's called apply async. And what that does is it says, call this function, but don't wait for the answer. Instead, just tell the other process to run it, and I'll come back later and get the answer. All right, so let's take a look at here it is. Oh, wait a minute, I've got a simple example here. So let's take a look at the code here for the pool example. So from the multiprocessing library, I'm only going to use the pool class. That's all I need. Now, the pool class, because of the way it works, you cannot use this inside of the Python interpreter. You have to literally run it as a script or as a program. And so inside of so whenever you run it as a program, you say if name equals main. That's the main method. So here you say create a pool of 5 different processes, and then and bind it to the variable p. Then say p.map. So map is a function which already exists in Python, which says apply this function to every element in some sort of iterable, like a list or something like that. So in this, it's going to create an iterable that goes from 0 to 199, right? So and the function it's going to apply is this one, start function for processes. Okay. Of course, you can name it anything you want. And so it's going to execute this start function for processes in these other sort of pooled processes. And for each one, it's going to pass one of these numbers over to that process and execute it. There's an optional parameter here called chunk size. Okay? And by default, the chunk size is 1. And what that means is it's going to take these numbers, going from 0, 1, 2, 3, 4, and one by one, it's going to send them to all the to all these 5 processes. So it'll take the number 0 and send it to process 1. Take the number 1 and send it to process number 2, and so on. Okay? Now, sending data one at a time, especially when it's a small data item, that can be very expensive. So you can improve performance, in this case, quite a bit by increasing the chunk size to say, don't just pass 1 item, I want you to pass 10 items at a time. Okay? Okay, so I don't think I have this in a file, so let me just copy this. And let's go over here and say example pool.py. And what I'm going to do is, I want to be able to see these things. So I'm going to say from timer import sleep. And right here I'm going to say sleep for 1 second. 1 second's a lot. Let's say half a second. That might still be too much. Okay, so let's look at my activity monitor. Right now there are no Python programs running. let's hope that this works. And let's time it just for fun. Oh. Is it timed? Yeah, it seems to work. All right, so take a look at my activity monitor. It's got a whole bunch of Python processes running now. Okay? So while this is working, let's take a look at the code. So what it should end up doing is after it distributes all these numbers to the different processes to execute this function, it gets back all the results as if you were to call as if you called a normal map function, right? And when you print them out, here's the result. So remember, what this is doing is squaring the numbers. So here we have 0, 1, 4, 9, 16, 25, all the way down to 39, 601. Excuse me. Okay, so we can see that the pool process actually works. So let's take a look at so what I've done here is I've modified the the Pi program to now use a pool of workers. So it's the same compute Pi function, but this time what I'm going to do is I'm going to run, let's see, that's 100 million. That's going to take a while. So I think last time I did I did 10 million. Well, this will work. Okay, so here's what's going to happen. It says create a pool of 4 worker processes, bind it to P, call p.map, send the function compute pi to those 4 worker processes, and send them this data. Now the data just says it's the number 10 million times 4, so it creates a list of 4 of these, and it just distributes them, 1 to each process. Now I could have made this, like a million times 10, and it would have created 10 sort of pieces of work and then distributed it to 4 processes. Maybe I'll do that and try it and see what happens. Notice that I didn't put a chunk size here, so the chunk size is just going to be the default 1. Once it gets it back, it prints out all the pi values that got computed, and then it's going to sum them together, divide by 4. I think that's right, and compute the error of this approximation. All right, so let's do this. So Python time Python 3 pi.py, and let's get my activity monitor going. Here it is. There are no Pythons. And now you can see that there are 4 Pythons that are running at like 50% CPU, right? So I don't know why it's not 100. And the total time is 14 seconds. And then over here, you can see that when I ran the Python 3 sequential pi, it only took 5.8, but that, of course, is only doing half of the work. It would actually be more accurate if I made this 40 million. So let me run that, and then we'll come back and see what the time was. And just to verify, there's only one Python program running at close to 100% CPU. All right, so let's let that run in the background. Okay, now with the pool, once you establish one of these pools, you can actually run it. You don't have to just do one map and quit. You can actually use that pool many, many times to do whatever you want. You can use different functions, different data, anything you want. They're just a bunch of processes sitting there waiting for you to use them. Okay, and so that's a good way to just sort of create a whole bunch of helpers and then start farming out work to them. All right, so let's see. We have a question. let's see, the question is, how does pool differ from queue? Yeah, so we're going to talk about a queue in a little while. Remember that a queue, all that is a data structure where you put things on one, like a tube, and you put things in one side, and then you pull things out the other side. Okay? And so we often use that for communication. What a pool is kind of a higher, sort of a higher level concept. It says that there are a bunch of worker processes, and you're feeding them work somehow. Now, usually the way people implement that is that they use a queue. They put all the work in a queue, and then the helper programs go into the queue and say, get me the next item to work on, right? But you can actually implement that pool in many different ways, depending on if it's a distributed program, a parallel program on a single machine, or if it's something like the thread pool implementation in Java or C#. All of those implementations are different. So the pool is kind of a high-level abstract thing. A queue is just a particular implementation of a data structure, which can be used sometimes to make a pool. All right, well, let's go back and see what happened. All right, so it says that running sequential pi, running 40 million of them, it took 23 seconds here, almost 24. And over here it says if I ran it with 4 worker processes, it took 14 seconds. Okay? Now you might be wondering, why didn't it go 4 times faster? And the problem is that it's pretty rare that you will see linear speedups like that, because there are a lot of things that are conspiring to make your program slower. So the overhead of communicating with these different processes and managing them, that's going to be one of the things that slow you down. The operating system is trying to schedule these processors, these processes, and so that's going to slow things down. So there are a lot of things that get in the way of getting pure linear speedups. And in fact, most algorithms, are not easy to speed up in that way. And so just throwing more processes at a problem, you might get some speed up, but you won't get, like an amazing speed up or anything. Okay. So you got to be careful, sort of judicious about how you use parallelism, not just in Python, but in any program. All right. So anyway, that's the pool. It's the easiest thing to use. The pool is actually using something called a process. All right. So in the process, what you're doing is you're literally creating another Python process, but there's no way to communicate with it just yet. Okay. So all you're doing is launching another process. And what you do is you say, okay, here is the function I want you to start at, the main function, whatever it is, and then you can give it 0 or more arguments passed in as a tuple. So that will call them. It will create a new process, call the main function, pass in the arguments, and run it. However, it won't actually run it until you manually start it. And then whenever you want to, whenever you're done with the process, it's a good idea to call join. And what join will do is it kind of like cleans up the other process and frees up any it creates something called a semaphore in order to manage these sort of child processes. And so p.join here is going to clean up some of the semaphores and other management data structures. All right. So here is a very, very simple example. It says down here, create a process, target equals prove existence, which is a function right up here, and there are no arguments. Now, in this prove existence, all I'm going to do is print the process ID. Okay? And so this thing is only going to have one function. Actually, I have another one. Let's see. Simple process. Here we go. So this one will create 2 processes. You see P is equal to process, and then P2 is equal to process. So let me run that. And Python 3 simple process. And you can see that when it prints it out, it says 516, 517, right? So, it is literally creating new processes, and you can get the process ID number so you can show that it actually works. However, we still don't have a way of communicating with it. So if you create another process and told it to do something, at this point you wouldn't get any answer back. So this is mildly useful if you have some sort of background job that needs to be run, because you can pass in arguments, but oftentimes you want to communicate with the process somehow. So one way to communicate is to use queues or pipes. Okay. So as the previous question just asked, what is a queue? Well, a queue is a data structure where you can send things. It's kind of like email. You can send things to another process by pushing it onto the queue, and the other process can then pop things off of the queue and work on those data structures, on those items. All right. A pipe, on the other hand, is actually two-way communication. So therefore, you can send things into the pipe, and then you can also receive things from the pipe. I don't know how to pause this thing. That's annoying. It'll go away. All right. But in order to make this work, you actually have to pass in the queue or the pipe whenever you create the process. So as part of the initialization, you have to say, here's the queue that I want you to use. All right, so here's an example. And I think I have this written up. So if we go through here, it says, from multiprocessing, import the process, because that's what we want to create, and then we want to communicate with a pipe. All right, so down here, we're going to create a pipe. So whenever you create a pipe, it creates the two different ends of the pipe. Think of like if you're talking on the phone with somebody, there are two phones involved, your phone and the other guy's phone. And so that's what you're going to get, is two ends of the pipe. So now what you do is you create a process, tell it what function you want to run, and then pass in which end of the pipe you want him to talk on. Right? So here it is, child. And then some extra data. So I just have a string to print out. Then you start the process, and then you send something into your end of the pipe. So this is the parent end of the pipe. So you send a string to it, and then it runs Ponger right up here. It goes up here, and it just receives. What it does is it receives a message. It prints it out and says, this particular process got this message. Then it goes to sleep for a second so that we can see it happening. And then it sends the string into the pipe and increments the count. And it does this for 100. All right, so this should be Pong. I don't know why I have two windows. So here we go. So here's the code, and let me run it. Python 3 pong.py. All right, so let's look at these numbers. We've got 18659 and 18658. There are only two processes, and they're exchanging messages, pong and ping, right? So ping pong, the game. And if we go over to the activity monitor, we can see that there are two instances of Python here, right? One is the parent that we created, and the other one is the initial Python program, right? The parent Python program. All right, so we've actually got, two processes communicating with each other using the system. While that's running, let's take a look at an example with a queue. All right. So here I wrote a different program which says if you give this process a number, a random number, it will tell you whether or not it is a prime number. Okay? All right, so let's take a look at the code. Down here, it's going to create a queue, okay? And that queue up here comes from the multiprocessing library, of course, right? So import process, comma, queue. So we got the queue. Now we create a process, and we just pass in the queue argument over here, all right? So that's process main, here it is, with the queue. This is going to run in an infinite loop, at least the while loop will. It's going to get something from the queue, and if the message is equal to 0, then it returns true. So this is what's called the sometimes called a kill message, right? It's sort of a secret message that we send to a process to say, maybe it's called a stop message. Yeah, but basically it's an agreed upon message that says you can shut down now. So that one is going to be 0. So if it's not 0, then it just calculates it is prime up here, and if it is prime, it'll print it out. So this will produce down here. So it starts the process, and it'll produce 100 random numbers between 0 and some big number with a lot of zeros. Okay. Once it's done, it'll put 0 on the queue. That's the stop message, and then it will do a join on the process to wait for it to stop. All right, so take a look at, this thing is still running, so I'm going to kill it. And Python 3, PQ. Okay, so it printed out some numbers here, and it's claiming that these numbers are prime. I have no idea if it's prime or not, because they're just random numbers. So the way we can figure that out is go to Wolfram Alpha, and say, is this number prime? And it says, yes, it is a prime number. Let's see. Okay. All right, so we've seen examples of using a pipe over here, and then also using the queue. Now, there are some, minor issues you have to be careful about. For the pipe, you can't have two different processes reading and writing to the same end of the pipe at the same time, because it's not. They didn't write it to be safe for that sort of concurrent use. So you do have to be careful about how you use the pipe. The queue is a little bit safer. You push things into the queue, you pop things off the queue, and they have a proxy that wraps it, so it's safer. Okay. Now another feature that they have is something like shared memory. But not quite shared memory. So they have two different things, a value class and an array class. So the value class, all it does, it's a single basic type. So int, float, bool, characters, that kind of thing. Okay? And think of it as like a global variable that all of the processes can see. Right? The array is basically the same thing, except it's a bunch of values, not just one. Okay. Now, the weird thing is that in both of these cases, you have to use something called a type code to tell Python what is the type of the thing that you're wrapping. So some examples are I for integer and D for double. Okay. And the other thing is that these are not thread safe. They're global, something that all the processes can see, but they don't have a lock on them, like automatically. So you would have to manage that yourself. So I think I have, let's see, I hope I have it. Yeah, okay. So here I've got, if you look up here, I'm using multiprocessing, importing a process and a value and a lock. Okay. However, I'm not going to use the lock right now. Although I've created it and I passed it in, I'm not going to use it. And what I want to show you is that in this example, I'm going to create two processes. And for both of them, I'm going to pass in the value. So notice how I create the value. I say it's an integer, and the initial value is 0. Okay? And then I just create a lock. I pass in the same value and lock to the two different processes. I start them both, and then I join them, right? And each of them are going to run counter. The counter just says increment from 0 to 9, right? And just increment the value. So in order to get the value of that, the value of the value, you just say c.value, okay? All right, and then at the end of it, it's going to print out whatever the value is. So if two processes are incrementing by 10, then the final value should be 20. So this is simple value. I put that half-second sleep in there. Oh, it did work this time. Wonder why. Ah, here we go. Well, the first time I ran, I got very lucky, and it worked. But the second time I ran it, I got 15. And I bet if I run it again, oh, 20 again. I wonder what's happening. Last time I ran this, I kept consistently getting like 11 and 12. Here we go, 13. Well, anyway, a program that keeps giving you different answers, that's not so great. Okay? And the problem is that the value is not thread safe. So what we can do then, since I already have it here, is use the lock to get isolated control over the counter value and then increment it. So I've saved it. Now let's run it. $20, but we were getting 20 before, so yeah, it should work. Yeah, so now I'm getting 20 consistently. So you might think, oh great, now we have locks. So that solves our synchronization problem. But the issue, not just in Python, but in any language, is that as you start using locks, here and there to protect code, these locks become performance bottlenecks. So you were hoping to write a parallel program to run your programs to make your program run much faster, but the locks are going to become bottlenecks in your program. So when you design these programs, you want to avoid using locks unless absolutely necessary. Okay? But when you need them, then it's really helpful. All right, so the multiprocessing library, what they did is they duplicated everything that's in the threading library, including all the synchronization tools. So we saw what the lock is. So they also have rlock, condition, semaphore, event, and barrier. Okay, I'm not going to go over what these are. They're kind of in depth. This rlock is a recursive lock, but basically they have all of the sort of standard synchronization tools available for you. All right. So let's see. I think. Let me just make sure that I showed you everything. All right. Okay. Now the last concept, which is a little more complicated, is that they offer something called a manager class. And the manager class is going to create a special kind of Python process whose job is to protect shared data values that all the other processes want to use. Okay, so like if I were to create 5 worker processes, what I can do is create a manager process and have, for example, a dictionary in that manager class, in that manager object. And so those 5 worker processes, they can reach into the manager class and start adding or start reading and writing things from the dictionary. What the dictionary will do is it will give everybody, all those worker processes, it will give them what's called a proxy object. And this is basically a safe, a thread-safe way of accessing the different data structures that you have inside the manager class, right? So they include value and array. They include all the same synchronization classes, right? And they have a list and a dictionary. You can extend the manager class to add anything you want. So you can create a subclass of the manager and have it protect like your own queue, have it protect objects, anything you want. The manager also has something called a namespace. And the namespace is basically like, it's like a bunch of global variables. All right. It's whenever you write parallel programs, it's a, whoops. All right. So whenever you write, parallel programs, you want to try to avoid using any sort of globals anywhere, really. Sometimes it's unavoidable, but you want to minimize it as much as humanly possible. So even though Python gives you, all of these different features, if you jump in and start using all of this stuff and having all of your processes communicate with the manager class, it will really slow your program down considerably because there's a lot of you have to communicate between processes. The proxies are going to have locks and so on. So it's not it's there, but you don't want to use it too extensively. All right, so let's take a look at some code. Let's see, simple manager. We have a question. Okay. Oh, is there? Oops. Well, I'll figure it out later. Thanks. Okay, so for the simple manager here, you see up here I'm importing the process and the manager. The manager is very simple. And by the way, the manager and the pool, they support being used with the with construct. And what the with construct does is it automatically will clean up the manager once you escape the, the context of the with. Okay, so once you get done with the with statement, it automatically cleans up the manager. So here, what we're going to do is, using this manager, we're going to create a dictionary, and then we're going to pass the dictionary into 2 different processes. And what they're going to do over here is they're going to get their own process ID, and they're going to update the dictionary and say, initialize it to 0, and then just increment their own location in the dictionary. Okay, so it starts up both processes, then it waits for both processes to end, and then it prints out the dictionary. All right, so let's see how that works. And before I run this, let me get the activity monitor up. Because if you look at this, when I run the Python program, in the terminal, it's going to run one Python process. Then it's going to create a manager, so that's a second process, and then 2 processes, so process number 3 and number 4. So, darn it. Whoops. Sorry. So right now I have 0 Python processes, and hopefully... So now we have 4 Python processes, just as I had said. They're going to run. They spend most of their time sleeping. And here we have, it says the process ID 19333 is 10, and here 19334 is also 10. So they were able to, both processors were able to update a shared dictionary that's inside the manager process, and then the main Python program, which I ran right here, that was able to look at that same dictionary and print it out. Okay? And in fact, I think we can see, so here are the IDs, 193, 63, 65, 64, and 62, right? So 2, 3, 4, 5 are the IDs. So it says here 4 and 5 were the 2 processes that I created. So that means 3 was probably the manager, 19363 was probably the manager, and 19362 is probably the main Python program. All right. On this last bullet point here, I had a demo where, so here's what you can do. This manager object, let me come over here and I'll just show you. All right. Whoops. Here it is. Yeah, so the manager object also supports remote access. Right now, I'm using the manager object all within a single program. But what I could do is just launch a manager object and then write other Python programs that connect to that manager and start using the dictionaries and the arrays and all that stuff. And in fact, I can actually run other programs on other machines and have them connect back to the manager program and share data, write things and read things. So I had a demo where, I ran the manager on the Mac, and then, over here on Linux, I would run a client, and over here I actually ran 2 clients, right? So I could put things, I could get things from the queue and all that. But then, you know what? It's really complicated, and I don't think it's really a good idea to use this library. But I'll just explain it real quick to show you what's happening. Over here, they create a queue, but not the queue from the multiprocessing class, just an ordinary queue from the queue library. And then what they do is this weird thing. They create a subclass of something called the base manager. Okay? And they register a name called getQueue, so that whenever somebody executes getQueue, it runs this lambda, which all it does is return a queue, the queue that you just created. Okay? So this is kind of like dynamically creating a method on this queue manager class. Then it says instantiate an instance the queue manager on localhost listening on port 50,000. And they also require an authorization key, which is just any random string. Like if you put developmentor there, that would be fine. And so then you get the server and serve forever. At this point, the process kind of like it hangs, right? Your command line at that point hangs because it's just actively listening on this port for anybody to call. So then on any client, you can just do the same basic steps where you say create a queue manager, register the name getQueue, and then this time you're going to access it and say, here's the IP address, here's the port number, and I want to connect to it. So it's literally going to make a connection to the queue manager you created right above here. Then it calls getQueue, and you have a queue, and you say put something in the queue. Another client would basically write the exact same code, except they can call get on the queue, and they would get the value. Okay. Now, so the reason I didn't want to go into too much, I didn't want to do a demo for this, is because, if you're writing programs that span, that are distributed programs that use multiple machines, there are other libraries that can do a better job of managing that. So what most people would do at that point is write services with a REST API and have it communicate that way. Or they would use a more complicated queuing system like RabbitMQ and use that as the infrastructure for communicating between all of your Python processes. Rabbit will be able to handle enormous numbers of messages. It's reliable. It's got security features. It's got all kinds of fantastic things. Whereas this remote manager is very, very primitive. If all you wanted to do was, for example, if you had a production program where you had a bunch of machines and they wanted to share configuration information, right? Then you might think, oh, well, I could just use this dictionary and stick configuration information in there. But even that's not really a great idea. Instead, you should use something like Zookeeper because it's really designed for that sort of thing, and it's extremely reliable, and it would take a lot for one of those things to fail. But this thing could fail at any time. All right, so yeah, don't use this. All right, so. All right, so that's my last slide, and I didn't have a summary slide, so that's too bad. But anyway, that is basically a whirlwind tour of the multiprocessing library. So the thing to remember is, there are two primary ways of using it: the pool class, which is the easiest one, or the process class, where you have to do a lot of things manually. Set up a queue or a pipe to communicate. And then start sending and receiving messages. So try to use the pool class if you want. That's probably the easiest thing to use. The other thing, though, which I forgot to mention, is that you have to be careful about when you use this library. You only want to use it when your program is CPU bound. But the reason that Python is so popular is because programs are not usually CPU bound. Programs are usually I/O bound. So either the network is too slow, the hard drive is too slow, the web server is too slow, something like that. And so, in those cases, just running one instance of Python is going to be fine. But if you are running, something that is CPU bound, then this is an easy way to make use of all the cores on your machine. All right. So that gives us a few minutes. If you have any questions, please feel free to type them in. Let's see. Otherwise, next month, I think the end of August, I'll be doing another talk on async I/O, and that's actually, maybe a bit more useful than multiprocessing for the kinds of programs that Python excels at. And what asynchronous I/O will do is something like, I need to listen to 20 open sockets, and whenever data comes in, I need to process that data and send back a message, right? So with the async I/O, you can actually do lots of asynchronous operations at the same time, even though they're running on a single thread. And Python 3.5, I think, just came out, and they introduce the async and await keywords, which were first introduced in C# a few years ago, I guess 5 years ago. And so Python finally just got that, I think, a few days ago. All right, so yeah, so if you need to do that kind of operation, the async I/O library is really much better for that. Okay, well, it looks like there are no questions. In that case, hope you learned something during this little webinar. And remember that the webinar will be available in about 2 days up on our website. And, I hope you will come by and attend another webinar.